When Elon Musk walks onto a stage and unveils a humanoid robot, the world holds its breath. It's a moment ripped from the pages of science fiction, promising a future where mechanical beings handle our chores, perform our labor, and fundamentally reshape society. This is the promise of Tesla's Optimus, also known as the Tesla bot. But when that same robot shuffles awkwardly across the stage, its movements slow and deliberate, a different question emerges through the spectacle. Are we witnessing the birth of a genuine technological revolution, or simply a master class in marketing and hype? The debate surrounding Optimus is one of the most polarized in modern technology, pitting staggering ambition against tangible reality. To find the truth, we must move beyond the flashy presentations and examine the core technology, the business strategy, and the immense challenges that lie ahead. The vision for Optimus is undeniably grand. Tesla is not proposing another single-task industrial robot arm or a specialized machine for warehouse logistics. The fundamental premise of Optimus is that it is a general-purpose, bipedal humanoid robot designed to operate seamlessly in a world built for humans. This is a critical distinction. The argument is that our entire civilization, from the height of our stairs and the design of our doorknobs to the layout of our factories and the tools we use, is optimized for the human form. Therefore, the most versatile and useful robot must mirror that form. Tesla's stated goal is to create a machine that can perform unsafe, repetitive, or boring tasks, ultimately aiming to produce millions of units at a cost low enough to make them accessible to individuals and businesses alike. They claim this will address global labor shortages and free humanity from mundane work. This vision is powered by Tesla's existing expertise, particularly in artificial intelligence, battery technology, and electric motor design, all leveraged from their work on autonomous vehicles. To understand the case for Optimus as a genuine innovation, we must look at the unique advantages Tesla brings to the table. The first and most significant is the artificial intelligence and neural network foundation. Unlike many robotics companies that focus primarily on hardware and kinematic control, Tesla is approaching the problem from the brain first. Optimus is intended to be powered by a vastly scaled-up version of the same neural network technology that underpins Tesla's full self-driving FSD system. This is a monumental advantage. While a robot like Boston Dynamics' Atlas performs its stunning parkour through meticulously pre-programmed motions in dynamic control systems, Optimus is being designed to learn from and understand the world. It uses a vision-centric approach, processing data from cameras to identify objects, assess environments, and make decisions. Tesla's vast real-world dataset, collected from its fleet of millions of vehicles, provides an unparalleled training ground for teaching an AI about the complexities and unpredictability of human environments. This focus on creating a general intelligence that can perform a wide variety of tasks, rather than executing a narrow set of predefined actions, could represent a paradigm shift in robotics. The second pillar of innovation is the relentless drive for cost reduction in manufacturing at scale. Many of the humanoid robots we see in research labs are essentially hand-built prototypes costing millions of dollars. They are technological demonstrations, not commercial products. Tesla, with its core competency in mass manufacturing, is targeting a price point that is almost incomprehensibly low. For a machine of this complexity, Elon Musk has suggested a future cost of under $20,000. This ambition forces a completely different design philosophy. Every component, from the actuators in the joints to the battery pack and the structural frame, must be designed for high-volume, automated production. Tesla is leveraging its expertise in power electronics and lightweight materials to create a platform that is not just functional, but manufacturable. This focus on economics is something no other company in the humanoid robotics space can match at this time. It's the difference between crafting a single exquisite watch and building a factory that produces 1 million reliable timepieces every year. Third, we have the vertical integration and technology transfer. Tesla is not a startup building a robot from scratch. It is a vertically integrated behemoth with deep expertise in critical areas. The electric motors and power management systems in Optimus are direct descendants of those used in Tesla's cars. The battery technology is an evolution of the cells and packs used in its vehicles and energy storage products. This shared technology stack provides a massive head start. The company's experience in thermal management, sensor fusion, and low-power computing all feed directly into the Optimus project. This synergy allows for faster iteration and potentially higher reliability, as many of these components have already been tested and refined in the demanding environment of a production vehicle. However, the case for Optimus being primarily hype is built on a foundation of immense, and some would argue, insurmountable challenges. The most visible and frequently cited criticism lies in the public demonstrations. The unveilings of Optimus prototypes have been met with a mix of awe and derision. The robot's movements have been slow, clumsy, and fragile looking. It has shuffled across the stage, struggled with simple object manipulation, and appeared a far cry from the dynamic, capable assistant portrayed in Tesla's promotional videos. To critics, these demos reveal a technology that is still in its infancy, a research project that is decades away from practical utility, not a product on the verge of mass production. The stark contrast between the fluid, athletic movements of Boston Dynamics robots and the cautious, deliberate actions of Optimus fuels the argument that Tesla is far behind in the core mechanics of robotics, and that its presentations are designed to generate headlines rather than demonstrate genuine capability. The second major critique targets the fundamental design choice, the humanoid form. Why build a bipedal robot? Critics argue that this is a solution in search of a problem. The human body is the result of millions of years of evolution, a compromise of capabilities that is incredibly difficult and inefficient to replicate in machinery. Bipedal locomotion is an unstable and energy-intensive process. Creating a robot that can walk on two legs without falling over on uneven ground, navigate a cluttered room, or get up after a fall is a problem of nightmarish complexity. For most practical tasks in controlled environments like factories and warehouses, a wheeled or tracked base with specialized manipulators is more stable, faster, cheaper, and easier to control. The pursuit of a humanoid form, in this view, is an indulgence driven by science fiction appeal rather than practical necessity. It introduces a host of unnecessary engineering challenges that simpler, more purpose-built robots avoid entirely. Perhaps the most significant hurdle, one that transcends engineering, is the grand challenge of artificial general intelligence. This is the core of the hype versus reality debate. Tesla's entire strategy hinges on creating a robot that can understand and navigate the unstructured chaos of the human world. While Tesla's FSD-AI is impressive, driving a car is a constrained problem. The vehicle operates on a defined road network, follows a set of traffic rules, and interacts with a limited set of object types, other cars, pedestrians, signs. The world of a general-purpose humanoid robot is infinitely more complex. Interpreting a command like "tidy the living room" or "assemble this piece of furniture" requires a level of common-sense reasoning, contextual understanding, and physical intuition that is currently beyond the reach of any AI system. It requires the robot to build a sophisticated model of the world, understand the properties and functions of thousands of objects, and plan complex sequences of actions with an understanding of physics and cause and effect. Many leading AI researchers believe we are still decades away from achieving this level of artificial general intelligence, making Tesla's ambitious timeline seem, to many, like pure hype. Finally, there are the economic and societal questions. Even if Tesla overcomes the technical hurdles, will Optimus be economically viable? Can it truly perform tasks more efficiently and cost-effectively than a human worker or a dedicated machine? In conclusion, the truth about Tesla's Optimus is that it is a Rorschach test for the future of technology. What you see in it, a revolutionary breakthrough or an overhyped distraction, depends on your faith in Tesla's AI strategy, your assessment of the challenges, and your timeline for technological progress. It is real innovation in its architectural ambition, its focus on scalable manufacturing, and its audacious goal of creating a machine with general intelligence. Yet it is undeniably hype in its presentational gloss, its promises that dramatically outpace its current abilities, and its potential role as a strategic narrative for the company. The final verdict will not be delivered on a stage in California, but in the years to come, on factory floors and in homes around the world. It is a project that forces us to confront the furthest edges of our technological capabilities and the very future we wish to build. The story of Optimus is still being written, and its ultimate chapter will determine whether it was a visionary leap or a cautionary tale of ambition outstripping reality.